Well, as we approach 4 from the left, we're approaching 3/4 of 4, which is 3. And as we approach 4 from the right, we're approaching -4 plus 7, which is 3. So the left and right hand limit are equal to each other, so the limit does exist. This is not the false answer that we look for. How about f of 4? When x is 4, f equals 2. That certainly exists. That's not the false statement we're looking for. What about f is continuous at 4? To be continuous, the left and right hand limit must exist and be equal to f at f4. Well, at 4, it's equal to 2. The limit as we approach 4 is 3. Therefore, E is the false statement. Number 2. As x approaches 2 from the left, we're coming up on it on this side. We can substitute 2 in there. We're approaching 4 minus a squared times 2. What about part B? As we approach 2 from the right, this is when x is greater than or equal to 2. So as we get closer and closer to 2, we're getting closer and closer to 4 minus 2 times 2 squared, which is -4. All right, part C, find all the values of a that make f continuous at 2. Justify your answer. If f is continuous at 2, then the left-hand limit and the right-hand limit will equal each other. So we have 4 minus 2a squared will equal -4. So -2a squared is -8. A squared is equal to 4. A can be positive or -2. That's it. All right, how about number 3? Well, you won't be able to evaluate this one using Calculus AB material. That's why technology was allowed for this one. If you graph this function, you'll quickly see that as x approaches 0, this is approaching 1. If you're wondering, how can we evaluate this limit? It should be an easy way since the answer is so simple. Well, you could do this with Taylor series. There's nobody in AB calculus that could evaluate this limit with algebra. They could only do it with technology. But you guys in BC, you could represent this expression with a series and easily show that the limit was 1. In this case, using your calculator again, or series, why not use your calculator for Chapter 1 and Chapter 2 tests? It's a lot faster too. This limit is approaching 2. So we might focus on the fact that 2x minus 1x was 1x, and 4 take away 2 is 2. So guessing that this limit is going to be p minus q. And since you're using technology, you can easily check that. Put in 7x minus x, or 7x minus 2x, and see if the limit is just 7 minus 1 or 7 minus 2 or whatever it is you try. All right, technology allowed. That made this one very nice. All right, number 4. Let's look at this function where n is an integer and see if we can answer a, b, and c. All right, so if n is 2, this is our function, and if n is -2, this is our function. For the horizontal asymptotes, those are always the end behavior asymptotes. So as x approaches infinity, what is our function approaching? We can ignore the 2x and ignore the 1. It's approaching x over x cubed, which is 0. So the horizontal asymptote, y equals 0. When n is 2, and when n is negative 2, it didn't matter. As x approaches infinity, this function is approaching x over x cubed, which is 1 over x squared, which is also the horizontal asymptote 0. As x approaches infinity, 1 over x squared is approaching 0. For part B, n is 1 or n is negative 1. Factoring the denominator, Okay, vertical asymptotes are when the denominator is 0, but it's not a 0 factor, which cancels out with a similar factor in the top. So when x is 0, x doesn't cancel out with any x factors on top, because you have to treat that numerator as a sum. So there will be a vertical asymptote when n is 1 at x equals 0. And that's it. Because x squared plus 1 will never be 0 with real numbers. When n is negative 1, factor, and now x plus 1 cancels out with x plus 1. So even though x is equal to, or the denominator is 0 when x is negative 1, that's really just going to be a removable discontinuity. So our vertical asymptotes will be when x is 0, when x is 1. All right, that's it for part B. Now let's get to part C. Well, if we factor that denominator, we get x times x squared plus n, and there will always be a vertical asymptote at x equals 0. It doesn't matter what n is equal to. Alright, so when n is greater than or equal to 0, this factor will never be 0. Positive plus a value of n greater than or equal to 0, it will never be 0. So it can only have a vertical asymptote when x is equal to 0. That's why there's only 1 when n is greater than or equal to 0. Alright, but why would there be 3 when n is less than or equal to negative 2? Why for these n values will there be 3 vertical asymptotes? Well, let's think about this denominator. When will it be equal to 0 for n values that are less than or equal to negative 2? We know that there will be a vertical asymptote when x is 0. Will this factor be equal to 0? It was never 0 when n is greater than or equal to 0. But if n is less than or equal to negative 2, let's see if there's any solutions. Let's subtract n from both sides. And now, if n is a negative value, then the opposite of n will be a positive value. And when we take the square root of both sides, we are taking the square root of a positive value. So we'll have 2 different solutions, none of which are going to be 1. Because if this was, never mind. So there you go. There will be 2 values of x that make this factor 0. And that means there will be 2 extra vertical asymptotes for a total of 3. We're done with number 4. All right, how about number 5 with no technology? The denominator cannot be 0. Factor it. Neither factor can be 0. So as long as x is not negative 4 or positive 2. So the domain would be all values of x as long as x is not negative 4 or 2. All right, what about the roots of f? Roots are tantamount to zeros. So finding the roots, we'll be finding the x values, which make f of x 0. F of x is 0 when the numerator is 0. And when you solve this, we have x is 2 or negative 2, but beware, don't assume those are both roots. Remember, whenever you have a rational function, you should factor everybody. So the numerator factors, the denominator factors, and that factor of x minus 2 is where there will be a removable discontinuity. So there actually won't be a root at 2. If x was equal to 2, this function is not even defined there. So there's only one root, and that's when x is equal to a negative 2. All right, as x approaches infinity, this just approaches 5. If you ever wondered why we can say with certainty that as x approaches infinity, we can ignore these irrelevant terms and just focus on 5x squared over x squared. If you took that expression and multiplied by 1, this over itself, then we would have, after distributing, we'd have this expression. And as x approaches infinity, this is approaching 0, and 2 over infinity is approaching 0, and 8 over x squared is also approaching 0. All right, let's move on to number 6. These are fairly self-explanatory. Using technology where it says it's allowed, we can determine that those are B and C. For number 9, this should look an awfully lot like the classic ones. Wait, is there a 2 there? Well, if there's not a 2 there, then this is just sine of x over x, and 1 minus cosine of x over x. And as x approaches 0, we know that approaches 1, and this approaches 0, so undefined. But I think that's actually a sine squared. So let's back up a little bit. So using the strategy of multiplying by the irrational conjugate, the denominator just becomes sine squared. 1 minus cosine squared is sine squared, because remember the Pythagorean identity, sine squared plus cosine squared is 1. So 1 minus cosine squared is sine squared. So this denominator will cancel out with that. And then as x approaches 0, this is approaching 1 plus 1. It's pretty simple. What about this one? As x approaches negative infinity, how would we deal with that in a nice, efficient way? Well, multiplying by e to the x over e to the x, you'll have to distribute. And when you distribute, we end up with this expression. And as x is approaching negative infinity, we can ignore the constants 3 and negative 1. And that just reduces to a half. All right, how about number 12? As x approaches 0, whether from the left or from the right, it appears that f of x is approaching infinity in both cases. So the left-hand limit is equal to the right-hand limit. We would say this is infinity, so there really is no limit. All right, so this left part approaches 18, and this right part of the compound inequality approaches 18 as x approaches 3. So that means the middle part, as x approaches 3, by the squeeze theorem, must also approach 18. So Roman numeral 1 is true. Now as x approaches 3, this is 9. So the limit of g as x approaches 3 is equal to 18 divided by 9. Therefore 2 is true. So that leaves us with 3. Well, if you think of x squared as x times x, then we can divide both sides by x and have 18 over x. But then we're taking the limit as x approaches 3. So the limit of x times g of x as x approaches 3 is equal to 18 divided by the limit of x as x approaches 3, which is 6. So 3 is true also. So the final answer is E. Number 17, if we're talking about the graph from number 16, then it does not exist.